Sorry. Okay, so the next topic then, and this was just a very introductory piece of information for our common ions. The next one we were going to talk about then is buffers. And in the buffers topic, we introduced a pretty useful equation called the Henderson-Hasselbalch. Which says that a pH can be calculated for a buffer, pKa, plus the log of our base concentration over our acid concentration. Something to remember about Henderson-Hasselbalch's equation. These guys mean concentrations. We do concentrations in moles per liter. pKa means what? Negative log of a Ka. pH means what? Negative log of the concentration of H+. Okay, don't forget some of the rules for this particular thing. One of the things we also talked about with buffers was polyprotic acids and how they are affected using the Henderson-Hasselbalch. So we saw something that had 2 protons initially, lost 1, and then the second proton is the one that was being removed. So do remember that when we see that happen, that we have Ka1 and Ka2, in order to remove the second proton, we should be using the second Ka, is what we're saying. So depending on the acid-base reaction we might be doing, we might be using, say, this particular reaction of acid and base. We might be using this particular reaction of acid and base. Depending on the actual reaction you're using, that's what determines the Ka. What else did we learn about Ka values? For the most part, you have to be given them in these types of equations, right? Or you have to solve for them. A lot of times you will be given a Ka so that you can actually calculate a pH. That is what the purpose of a Henderson-Hasselbalch problem is. Okay? Yes?
Are there some examples of that in the book, like in the blue?
Yes. We're also going to do practice problems.
Okay.
As most of what today is practice. Yes?
Do we have to have this equation memorized as well?
Never. It's the one equation in this chapter that you will be given. All right. Next up is going to be a titration curve. Okay, so before we move on to titrations, what is the purpose of a buffer?
To keep pH within a certain range?
Correct. It is to resist large changes in pH ranges, right? So a buffer, if designed well, will keep your pH of your solution within 1 point. Okay? If designed well, it is designed to resist large changes in pH. Okay, good. All right, moving on. Titrations, of which you're all intimately familiar. All right. And one of the things we are going to aim to do today is to make our pH curve from the lab that we did. With our titrations, okay, remember that the goal was to figure out an unknown concentration. And so we looked at curves of titrations where, for the most part, we added a strong base, okay? Could we add a strong acid instead? Absolutely. We just need to make sure we know what the actual reaction is before we start. Here we have ml of NaOH added. Let's say this is a strong acid with a strong base. Okay? So remember that what our titration actually looks like. We put something in the beaker, like we did in lab, like a strong acid, if you will. Then we add some amount of NaOH. Typically, we know the concentration of the NaOH, or we know the concentration of what's in the beaker. Okay? Those are the two things that we can start with that we know. All right? In this particular case, we're going to go with we know what the concentration of NaOH is. It's going to be 0.1 molar. In the case of a strong acid, strong base, what does this curve usually look like? Starting with acid in the beaker, so where should our pHs be first? Low. Eventually, with a strong acid, strong base, we shoot up, and then we level off again. Okay? So the way a strong acid-base curve looks is very stepwise. Okay? With a weak acid, strong base, how does this change? Right, our pHs start a little bit higher. Weaker acids are going to start a little bit higher, a little bit easier to change the pH of as you add a strong base. Eventually, we're going to get something that kind of levels off, just like it did in the previous one. And we're going to see that kind of curve, or that steeper hill, or whatever, at the beginning. Okay. So how do titrations work? Let's say we're doing strong acid, strong base first. The reaction for a strong acid, strong base is to take the proton, add it to the hydroxide, and form water. Okay. And I'll remind you that when we did these, we talked about ice tables again, right? My initial information was whatever was in the beaker. So in most of them, we started with acid in the beaker, right? Say we started with a certain number of moles. Okay, that was one thing that we started with in our ice table. We started with moles in the ice table. We assume that all reacts, right? So if we only have 5 moles of base, but we started with 7 moles of acid, that 5 moles of base is going to completely react with as much acid as it can, and it's going to leave behind whatever's left over, right? It's going to leave behind your 2 moles of acid in that particular case. So just remember some of the basics behind these. Again, we will practice with them here in a second, but I just want to remind you of some of the major things you have to remember. Once we get our final information, we convert our moles to molarities by dividing by volume. So that's our approach for strong acids and bases. What is our approach for weak acids? Or weak bases, I guess. There was an additional step. Anybody remember? Can I erase? Weak acid, strong base. Okay. So first things first, write out the actual reaction. So let's say it's a weak acid. Unfortunately, we can't just write H+, right? Because with a weak acid, not all of it is going to just completely react with OH. What actually ends up happening is we get HA plus OH minus, leaves behind the conjugate base of that weak acid. From there, we do similar things that we did in our previous titration. Let's say we start with, I'm going to use easy numbers if that's okay. 10 moles of HA. We add, how many moles do you want to add of the OH minus? Let's go with 2. 2 moles of OH minus. All right, after these two things react, what's left over of the HA? 8. What's left over of the OH?
0.
Nothing. What happens on this side? Oh, yes, something happens on this side. This is the difference between the two. Is that when we use a weak acid base, we cannot assume that these two things are just going to cancel each other out. We have to remember that they're going to form a conjugate base situation. Okay? From there, the next thing we do is put those two things into molarities, right? Because remember, we're dealing with moles here. And then we use an equilibrium expression. Since we're dealing with a weak acid, we're going to use the weak acid's Ka expression. In that particular case, what would the normal Ka expression be? Do you get it from here? No, you do not. This is not the weak acid dissociation. This is the part that's different. You have to write out the acid reaction in order to actually get the correct Ka expression. The goal here is to find this H plus concentration. Okay, so for weak acid, weak base, we always start with the acid-base reaction. Okay, that's what we did up here. We're going to do the ice table with moles. We're going to convert, so far the same, the moles to liters by dividing by the final volume. Then we have to get a Ka expression. That Ka expression comes from the weak acid with water expression. From there, calculate H plus concentration using Ka. So there's two different ways of doing titrations. Okay, one involved just a straight, this much is going to react with this much. Strong acid, strong base titrations. Okay. The other way is a little bit more complicated, involves a couple extra steps. Okay. In this particular case, if we get to this part, what numbers should we be plugging in? Don't we have concentrations of A and HA? We do. Would we theoretically have a Ka? You should. If you don't have a Ka, you can't go any further with this. Okay? So we take our concentrations at equilibrium from the actual acid-base reaction. We're going to plug those guys in. We have Ka, let's say it's 1.8. Something along those lines. Our H plus in this case is the unknown. It's the thing we're looking for. Why are we looking for H plus? Because we're trying to find pH. The goal of any titration reaction or any titration calculation we're doing is to find a pH at a certain point along the pH curve. Okay? You're assuming, and I will assume, you don't know this. You do not know the exact pH curve for every single acid-base reaction you're going to do. You're not supposed to. But we can form one knowing concentrations. That's all we need is concentrations. And so now with your lab, you've actually calculated the concentration of the acid and of the base that was added. So we can make our own titration curve. So we're going to work on towards the end of class today. Okay? All right. erase this. All right. Last two topics involve KSP, which we talked a little bit about yesterday. Did some practice with. Okay, go ahead.
When with acid strong base reactions, what exactly are you solving for?
pH, same thing. You'll either have leftover H or OH to get pH or POH. All right, next up. Ooh, I forgot to talk about equivalence points. What is an equivalence point?
That middle on the graph. Middle.
This guy. What do we know at the equivalence point?
Middle.
Thank you. Okay, for strong acid, strong base, what is the pH at equivalence going to be? Nice. For weak acid, strong base, what is pH going to be? Greater than 7. For weak base, strong acid, pH is going to be less than 7. And these are all at equivalence. Okay. All right, slightly soluble salts. First things first, we have to be able to write a reaction. So if I give you a slightly soluble salt, you can tell me what it should dissociate into, right? What should this one break down into? Please don't forget that the number of atoms you have on this side has to equal the number of atoms you have on this side. Don't do this. Please, please don't do that. You are all graduates of the honors chemistry program and know common charges from the periodic table. Whether you remember them or not, you know that F is not going to be F2 in a reaction like this. All right, so once we have this, what other information can we talk about? Can we write a K expression? What's going to go with the K expression?
CAF squared.
Don't forget your rules for equilibrium. CAF2 has no business being in there, right? Because it's a solid. Okay, from here, equilibrium chemistry in a nutshell. You can use ice tables. If you're given concentrations of things over here, you can calculate K. That was one of the types of problems we did yesterday. If you're given something over here, you don't know what this is, but you know KSP, could you calculate the X's? Absolutely. The molar solubility of the salt was one we talked about yesterday. Molar solubility is just going to be a 1-to-1. So whatever the solubility is of this one at equilibrium is going to be the solubility of this guy at equilibrium, right? In this case, it's just the concentration of Ca2+. Okay. You could convert molar solubility to mass per volume, right? Given a molar mass. Convert moles to grams. Okay. I mean, I don't feel like I need to say a ton about this because we talked about it yesterday. But we will do more practice with it later. Yes? Good? Okay. All right, let's go back to common ions and do some math. Because there were some things we introduced in this chapter, like ignoring changes in X, that might be something we want to go over again. Talked about the rules for that yesterday, didn't we? In order to ignore X, what is the rule? Must be two magnitudes lower than the thing you're actually subtracting from. Okay. So the reaction And I am doing end of chapter problems in case you want to follow along and you have a book handy. If not, I'll just tell you what number they are. I have the 12th edition in front of me, so take that into consideration. First one I'm going to do is 17.15. It says use information from Appendix D to calculate the pH of a solution that is 0.060 molar in potassium propionate and 0.085 molar in propionic acid. Those two things, C2H5, no, C3H5O2. So this is the sodium propionate, or potassium propionate, sorry. And then the acid form puts an H on the end. This one is 0.085 molar. And this one is 0.0, oops, I lied. Okay. First thing is to calculate the pH. So right now, is this a common ion equation? No. Okay, and here's why. There is no addition of any kind of ion. We're just told what we start with. And we're starting with an acid and a base. So first thing I would go and I would try to do is to get the reaction written out. I'm going to put the acid. When we write acids, I typically put a proton out front, not at the end, just so you can see what thing is actually going to end up leaving. Acid gets added to what? Water. And forms oh boy, chapter 16 coming at you. Acid plus water makes hydronium ion plus conjugate base. Our goal is pH. In order to do pH with this, what do we need? Of all these four things, what do we need? I need this guy, right? Does this one matter? Nope. Equilibrium. Sorry, is mine. All right, what are we going to do next? Let's plug in what we know. We're given initial information. This one's the acid. What do we do next? Molarities. We only have to be in moles for titrations. Add X's. Which side?
Right side.
Thank you. Okay, what are we missing? The very beginning of the problem, it said use Appendix D. What's in Appendix D? K values. The Ka for the propionic acid is 1.3 times 10 to the negative fifth. Got a little overzealous my X here. Okay, what am I going to do next? Let's get everything at equilibrium. So that's my expression at equilibrium for that one. That's my expression at equilibrium for this one. That one's X. What have I not done that I probably could have done at the very beginning once I got my equation? Say again? Write the K expression. Oh, I just... That's a 5. Next. We can ignore x in our changes area, right? We can't ignore this x. Gotta have something to solve for. But can I ignore this change in x over here? Can I ignore this one? I can. Where am I going to ignore those? You just tell me to ignore them, but what do I do with them? Let's plug them in. Then you math. Please don't say it out loud. Everyone in the room needs practice using a calculator at this point. Math. Math is not disgusting. It makes the world go round.
No.
Literally makes the world go round.
You're making us do math in your class, though.
I know, I saw it last night.
Yeah, I was joking.
Humans are so nosy about the world. Just happen to have, just let me die. That's like tuberculosis goes through if I don't have to learn lesson.
Sorry, Molly, do you have a question?
Wait, Chris,
Yeah.
Super.
They just bought property in Tennessee. I thought they did.
I do. I was not using hers at the moment. She might want it back though.
Yeah, I'll probably need it like.
No, I have one. As long as you have a block, you can use mine. This one. There's like 8 cords in my drawer.
Thought you were going to throw it for a second.
Yeah, I thought I was way lower than I was.
All right, Patrick, what number did you get?
I got 1.842 times 10 to the negative 5.
Yeah.
Caitlin, what'd you get?
I don't know like.
Oh, Emily?
I got the same thing.
Gavin?
I got the same thing.
Okay, that's all I care about.
Actually got 4.1.
Are we done?
666.
No, 6666.
What was the question?
Never done.
I don't know.
Oh, pH.
What is the pH? What do I do with this number?
Negative log.
Take the negative log. This is just part A of the problem.
How many are there? There's C.
B and C.
How many problems?
The next ones aren't that bad though. They actually use the common ion in the next ones. What's that?
I got it.
What'd you get?
4.74.
4.74?
Yeah.
Yeah.
What you got? All right, that was A. Part B. Sorry, part B says, calculate the pH of a solution that is 0.075 molar in trimethylamine and 0.10 molar in trimethyl ammonium chloride. So, completely different reaction.
Why is it a part D? Why can't it just be
It's
the
just multiple practice problems is what it is.
But it's part B.
Okay,
Part B of question 1.
part B of question 1.
Nothing to do with
You're
part
fine.
B.
It has nothing to do with that. It doesn't make sense.
It doesn't need to.
I'm running out of room.
You're running out of what?
Room.
I am sorry.
This much space to work.
It was easier than writing the equation. Which is C is 3. I knew that off the top of my head.
Yeah, okay, like you don't have them open in front of you. Which is what I told you to do. So thank you for doing what I asked.
You're only 3 bucks.
You said if we wanted to talk about.
I did. You're right.
Some of us just
Some of you are going to have a rough time in that quiz tomorrow.
I'm writing it down. I have a whole notebook.
All right, so this is the other guide. This is the trimethyl ammonium chloride. Has a concentration of 0.10 molar. All right, so what's our first step?
Here goes.
The actual equation. First things first. Acid or base? Base. When we write base equations, what do we add? H2O. A base is going to remove a proton from our H2O and leave behind what? OH minus. Plus the base with a proton. This is this. What happens with the chlorine? It's a spectator. Remember, we talked about spectators in this chapter a lot. It means they don't have an impact on the equation you're looking at. They don't have an impact on the equilibrium reaction. So we don't care about the chlorine. It's there to balance the charge. In this case, what should the charge be on this guy? It gained a proton, meaning positive. If I remove a chlorine, which is typically a -1 charge, what happens to this particular species? It becomes plus. Okay? All right, what do we do next? How about this? It did say use the appendix. What do I need the appendix for? Ka? Kb. You joke, but that's a thing. All right. Kb.
No, it's not. What's
Yeah,
it
it
for?
is.
What's it for?
I'll tell you when you're older. All right, the Kb for this is 6.4 times 10 to the -5th. What next? Let's write the expression. I like that. What goes on top?
Oh, wait, and then the acid thing.
Goes on bottom.
The thing besides water.
Trimethylamine. Okay.
It's a long word. It's really
A thing beside water. All right, what's next?
Plug and chug. No.
Write the ice table.
Ice. Plug and chug.
I'm just thinking of
Okay. In our ice table, the most satisfying thing to do is to figure out what you don't need. What do we not need? Water. All right. What goes in the I section? Here.
There. Up there.
0.075.
0.075. What about here?
The other one.
What about here?
The other one.
Wow, you guys are really good today. All right. What goes in the C?
X plus X and minus
Be more specific.
minus.
left side and right side. Plus X on right side.
What goes down here?
0.1 plus X. Then
We will. We're going to use our shortcut. Oops. Don't add zeros where they don't belong.
Oh my.
I could feel like Blair all the way over here. And I'm looking up.
Don't add zeros where they don't belong. All right. What else? What do we do next? We're going to take these numbers, right, at equilibrium, plug them into the expression. Ooh, be careful, I just write 1 point.
Yes, then your entire problem is right until you get to the answer. And the answer is just off by like.
7 0. Thank you. Yeah.
No, you gotta do that and hide it from me at the same
I can tell you.
Is that what you got?
You're blocking the equation.
Well, that's a pH, right? Or a POH? that you just calculated? Because that's an OH concentration.
Wait, is
So
it
take 14
0.5 or
minus that.
0.4?
And then tell me what you get. You'll be back on.
Where?
Yeah?
Is it 0.5 or 0.4 for the baby?
6.4 times 10 to the negative fifth. This one? Oops. Sorry. Thank you. Yep. That's, I mean, it doesn't look wrong. Hold on, let me see. I got a B. I got 4.8 times 10 to the negative fifth. Is that what you got? Yeah. Is that what you got for that?
Oh, for that. I got that.
Is that what you got, Kevin? Is that what you got, Zach?
Yeah.
Okay. What? Are we done?
No,
What you gotta do?
get the POH.
So negative
POH will be the negative log of that number. What'd you get for that number?
4.31, well, 2, I guess. Sorry, I forgot to round there.
That's POH, but we were asked pH, right?
Minus 14.
So what'd you get?
9.68. Sorry.
Oh, you're good.
That's all right.
Can't steal all the spotlight.
All right. You're gonna do C on your own.
Oh, no.
Oh, you poor baby.
I'm actually looking forward to it because I think I actually might know what I'm looking for.
Well, I'm gonna give you a different one actually. I'm not gonna have you do C.
You should give us the what's it called, the KA.
I will give you the KAs and Bs.
Okay.
I will give them on a quiz as well.
Yeah.
Good question.
Refer to your book.
Are we good with this guy? Are you gonna do one on your own? What's up?
When you polytropic
Yes.
you typically use K8.
You either use 1 or 2. It depends on the reaction you're doing. If the reaction you're doing is the Ka2, then you would use Ka2. Okay.
I'll probably just ask tomorrow if I'm
I mean, it's not something I would intentionally do, but it is something that might happen. You do.
All the strong acids.
What? Oh.
Every substance has ever existed.
Oh, we do?
In the KA.
pH.
In the KV. You literally have to get humans encyclopedia of chemistry in order to do that.
You don't like to get a video of that because that's
0.25 molar.
I finally finished. Ask me anything. And only that there I can't because I never learned English. I only learned English.
You didn't have enough room for English either.
All right. Get to it. You're given a Ka, so the type of equation you should write is an acid or a base. Acid.
I was gonna say base just get the point, but I messed up anyway.
Pardon the interruption. Since none of these students came when we called them this morning, the following students need to come to the main office immediately. Dalton Clody, R.J. Dalton, Jocelyn
I
Garcia,
didn't hear that.
Alan Smith,
I did.
Michael Taylor, Davita Widers,
I was like, you didn't go when you were
Christian
home?
If
Ottman,
you're making an
Kevin
acid
Galan,
one, would you put
and
the
Rodolfo
acid
Rodriguez.
inside?
Please come
Nope,
to the
the
main
acid starts
office
here.
immediately and
You add
bring your
water
course
and you form the
selection
H3O
sheet.
plus
If you have
and the
it
conjugate base, which is going to be this side.
to the office.
Does that make sense? The way you did it, you actually wrote it as a base.
So I need to do the opposite? of this?
Opposite.
Can I see the answer?
What is the answer? What did you get?
Do you want the pH or the
I
pO?
want the pH.
3.34 something.
You're off.
By how much?
0.2.
Well,
What's your X value?
4.5.
Oh, you know what?
times 10.
Never mind. You're probably not off. You're good.
I know I'm good.
My numbers are wrong in the book than they are in the. You're fine.
Like the formula?
So it should be the acid on the left. This is the acid. You flipped the equation.
Is everything else right except for this?
No, because it makes H0 plus, not OH minus.
I did look at it.
It should be HCOOH plus water makes the base plus H3O plus.
What is the answer?
Looks close.
What'd you get?
I'm not done yet.
What's your reaction?
HCOOH. I just saw in my head, so maybe inaccuracy plus water equals H3O plus HCO.
Subtract your 14 from your answer.
Boys and girls, that's your reaction.
I just.
Those of you writing the base, you should be writing the acid form.
I have a question.
I also have the same question.
So, why is it that the product has a higher initial value than the reactant?
Remember, they're starting, so it doesn't matter. It shouldn't matter whatsoever because it's a reversible reaction. Yeah.
When you're finished with done, can you come here first?
Yeah. What's up?
Oh, I was just making sure I did my ice table right.
Yeah.
The negatives are on this side.
No.
And
No,
then
they should be on that side. The negative should be on the opposite sides. Because this one is 0, you can't subtract from 0.
okay.
What do you need?
I wrote it on the desk. So I can't. I can pick up the desk and bring it to you. That's right. That's right. Can I use this to clean off the dust?
Yep. There's other ones on the. Is that one empty? Real quick, I'm going to walk you through how these things get scored. Okay? For your equation, you're going to get a point. For the pH itself, which is the final answer, you get 1 point. You get a point for the X value that you work out from the work, which you get a point for. You get the concentrations at equilibrium, meaning you filled out your ice table. Okay? Down here, sorry. You get your ice table actually set up. You get a point. And if you write out a Ka expression, you get a point. So a lot of what you're doing in this problem is going to get you points for setting things up correctly. Pay attention to this stuff. This is the stuff I'm looking for. Yes?
Tomorrow we mostly math, or will there be like multiple choice?
Usually there's a few multiple choice on each topic, and then there's a math problem for each. Good question. All right. What was the pH? 4.14.
Never mind.
Because you were solving for O instead of P instead of H.
No, that was
In that problem, it was the concentration of OH.
What did you end up getting then? As a That's what I got.
That's the answer.
The first one. So is this what you plugged in?
If these ones are this easy on the quiz, then I'm good.
Well, this is the first of the 4.
What?
There are 4 different kinds of things we talked about. The next one's
Wait,
quick.
with the
Yes.
common ion or-
No.
Oh, I was gonna say.
Common ion is just one of the 4.
If our our answer was 7.2 times 10 to the negative second, or just times 10, or no?
If this was wrong, your pH is off by like 3 units.
Well, no, I'm saying if it wasn't 2 magnitudes, we have to go back,
Correct.
and we'd have to plug that into X.
You would have to go back and you'd have to do the actual quadratic.
Okay.
Yes.
Please don't make me do that.
And that won't happen for the most part. Now that you've learned when you can ignore them, prior to this chapter, there were situations where you were not able to ignore them because their concentrations were very close. But in this chapter and beyond, you will be able to ignore them. Yes.
What formulas are we actually going to have to know that you won't give us on the quiz?
Unintentionally, I probably won't give you the pH, pKa formulas. I'll just assume you know that you have to take the negative log of a number. But that being said, if you ask me, I'll tell you that it's negative log of whatever. I'll probably write them on the board just to make sure. But that's the only one I can think of. Molarity? Moles per liter? Okay. How to go from moles per liter to moles? Multiply by volume, right? Okay. Stuff that I assume you can do from chapter 4.
Will you give us the conversion for grams to milliliters?
No, I will not. No, I will not. Can I erase and do a different one?
Can you write that?
Let's talk about buffer equations.
Can we take a break real quick?
Yeah, for 2 minutes.
Yeah, honestly, I'd rather.
You're just cutting into your own review time. I'm just saying.
I need this time.
I'm sorry. What I don't get through, I'm going to assume you know. Like, for instance, the KSP stuff from yesterday, I'm probably not going to get to that in class. You should feel comfortable doing it because we spent all that time doing it yesterday.
Would it be
Otherwise, I'm here after school.
Okay, I was gonna say, I'll definitely do that because I was going yesterday. It seems like that was not that hard though. It's just the dissociation and then whatever you do from there.
Did you say your driver?
So, I don't know. What do we do in history?
0.25
What
over
did we do?
0.1.
What did we do in history yesterday?
It's 2 point.
Here, look.
Oh,
we did a review
0.25 over 0.1.
We did another review thing.
Oh, no, does that mean there's like a test today? Or a quiz today?
No, it was like for the exam.
Wait a minute, what you
Oh my gosh, what
Okay, hold on.
Wait, at the end of the year. Oh, well, I don't
Okay, you're gonna do algebra again.
You didn't miss that much.
exam? Alright.
What do you do
I
next?
only take the class to chase the GPA.
You're going to move this over?
Because like, you know, my sister goes to Johns Hopkins University and they wouldn't have accepted any of them, any of the credits. No, most public schools will, but a lot of like big private schools won't accept it. It's crazy. They're like, nope, you gotta take it. Like my sister, she took the AP Chem exam and they made her take it, Chem again.
You had 7.2.
And it's a lot harder there too,
I
so.
think you
Skips
dropped
the
this
whole
one.
class.
You wrote it. You still multiplied it
I
over.
don't know. They might make me take Spanish then, too, because I only have 2 years underneath my belt. But as long as the only reason why I took Spanish in the first place is to, get into a college in the first place.
Yeah. All right, let's talk about Henderson Hasselbalch.
You can learn a different language than Spanish.
I'm going to remind you, with the Henderson Hasselbalch, I think the hardest part is identifying the acid and the base that you're given to work with. Okay? Please remember you have to have concentrations. So if you're given volumes and masses, you have to convert them to concentrations. What's the concentration for molarity? Or what's the formula?
Moles over liters.
Moles over liters. Don't forget that. Okay? Please don't forget that fundamental thing. It's very important. It's also very important that you remember that all volumes, even though they're usually given in milliliters, should be multiplied in liters. All right. Let's do this one. This is 17.21 is the one I'm going to work on from your book. This one says, calculate the pH of a buffer. That is 0.12 molar lactic acid and 0.11 molar sodium lactate. Okay. I don't, but you don't need them. And we'll talk about why. I need the Ka next is what I'm looking for, sorry. 1.4 times 10 to the negative fourth is your Ka. Okay, so first things first, which one's the acid? The one that says acid. And this is why it doesn't matter if you have the formulas, right? Does it matter what the formula for lactic acid is? Not even a little bit. You have an equation for calculating the pH of a buffer that says I need a concentration of a base and an acid. I was given the acid concentration to be 0.12 molar. What does that make the other thing? Hopefully you realize that that must be the base, okay? Because it's not the acid. The other reason you might notice this is the ion names. A lot of times our acids have something ic and our bases have something ate. Okay, that's a very common word association for acids and bases. Do I expect you to know that? Absolutely not. But in this particular case, could you reason this thing must be the acid and by process of elimination, this thing must have been the base? Yeah, cool. All right, next thing is we were given a Ka. What do we need in our Henderson-Hasselbalch in order to do this? I need a pK. So we're going to take the negative log of the Ka we were given.
3.85.
Thank you. All right, what's next? Well, I want to know the pH of the buffer, right? So can I just plug it in up here? I can. You see the term buffer in a reaction or in a problem. You should immediately be thinking Henderson-Hasselbalch. Okay? These do not apply to every acid-base reaction. Please do not use them for every acid-base reaction. You will get something wrong. That being said, if you see the term buffer, think Henderson-Hasselbalch. Can I ask you to solve for a pKa if I give you a pH and the concentration of an acid and a base? Absolutely. A lot of times I'll be asking for a pH or a pKa in this reaction. Could I ask you to solve for a base or an acid? Yes, I could, and you would hate me for it because you have to use the property of logs to figure it out. Well, like we did in class when we did this problem, which was like a week ago, and I guarantee you don't remember. I will talk about, if I ask you to do that, I would give you the property of logs on your quiz. It's basically just the log of, if they're divided, they subtract. Isn't that right? Who's my calculus people? Property of log says I can subtract them. Log of base minus log of acid is what it becomes. All right, so I'm going to plug stuff in. I was asked a pH. I now know the most common mistake in these types of problems is mixing up the acid and the base and putting the wrong number on the fraction. What'd you get, Ryan?
Hold on, I'm redoing it real quick.
Shelby? 3.82, 3.815.
I got 815.
Remember, a buffer, boys and girls, is supposed to stay within 1 point of the pKa. Did that work? Yes, it did. It did exactly what it was supposed to do. In reality, they're going to stay within 0.1, maybe 0.2 units of the original pH. Okay? Do we want more practice with this, or we feel pretty good?
It's fine.
Do you want one more? I can do one more.
You can do one more.
One more.
One.
One more, and then we're going to do titrations.
We just do one on like on our own, we can check in.
That's what I meant. Yeah, that's what I meant. That's fine. We can go. We'll move on. If you want more practice as an individual, when can you come see me? After school today, I will be here. I don't have anything going on after school.
Yes, you do.
No, I don't.
Yes, you do.
What is it? What? I'm getting a Frosty. I'm getting a Frosty.
I got the free frosty pizza.
Buffer equation right now.
I'm getting one for these boards. You got your time. Yeah?
Do some titrations. Oh.
I got it somewhere.
Titrations. I'm gonna pause and I'm gonna upload a separate video for titrations just so you're aware.